Whoa, that's like a new, did you guys hear that? That was different, right? No? Normally it always says like this meeting is being recorded, but it was like a new voice and a new phrase. Or am I the only one who got weirded out there? All right.
It's
Okay.
definitely new.
It was definitely new, right? Okay. Okay. I was like, what just happened? All right. Sorry, I almost had a little scare there. Okay. Well, it's Friday. It's Friday, and happy Valentine's Day, everybody. That's on Sunday, and happy Lunar New Year. So and we have a 3-day weekend. So I won't see you guys till Wednesday, and anyway, you guys will be fine. Okay. All right. It's been that way for a few weeks. Oh, it's with the new update. Okay. I guess I only recently updated. All right. Okay, we're gonna pick up and we'll cover IEEE 754. I think we started talking about this on Monday. Oh, and you guys took your midterm on Wednesday. Oh, so let me just talk about the midterm. I haven't even looked at it. Okay. So I'm gonna meet with my TA and readers, and we'll probably grade them. We'll try to grade them this weekend, okay? And then I'll post the grades. And then homework 3 has been graded. I just have to kind of publish those grades. So homework 3 will get graded. And yeah, usually after I grade the exams, I'll take a look. And again, my goal is for the median to be somewhere in the 80s, and if it's lower than that, I'll make a positive adjustment. And if it's higher than that, then good for you guys. So we'll see. I really have no idea how people have done yet. So okay. All right, so we're talking about double precision floating point. We got 64 bits, so we can represent a whole bunch of numbers. 11 bits go in the exponent, 52 bits for the mantissa, and 1 bit for the sign. And what we are doing is we are exploring kind of the same idea of the double precision floating point number, but with a miniature version. And in our miniature version, we have 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa, okay? But the same kind of ideas that apply for the mini float just apply also for the double precision and also single precision floating point and long double. It's just that you have more more numbers. Okay. All right. Okay. So we already talked about the sign bit: 0 if it's positive, 1 if it's negative, and then 3 bits for the exponent. Okay. And the concept of a biased exponent is a little bit strange, but if you however many bits you have, okay, the case where the exponent is all zeros and the case where the exponent is all ones are reserved for special cases. Okay. And then everything else in between, basically we need to split those, half of those to be positive and half of those to be negative. And so we kind of take the rest and we subtract basically half of that to get our bias. All right. And so the formula for figuring out your bias is 2n to the n minus 1 minus 1. Okay. But basically you figure out how many unique values you can represent, which is going to be 2 raised to the exponent. So in the double precision floating point, you have 2 to the 11. You can represent 2048 unique values. You reserve the all zeros and all ones to be special cases. So that leaves you with 2046. And then half of those are going to be positive and half are going to be negative. So your bias is going to be half of 2046, which is 1023. Okay. So the bias for the double precision floating point is going to be 1023. For our miniature floating point, where we have 3 bits, we can represent 8 unique values, 2 to the 3rd. The largest and the all zeros and all ones are special cases. The remaining 6 are going to be used for exponents, and we want half of these to be positive and half to be negative, or I guess non-positive, I should say. And so we're going to subtract 3. And so we do, 6 minus 3 is 3, 1 minus 3 is -2. And we can represent exponents anywhere from -2 to +3. So our bias is 3. Okay. Okay, and then we said 4 bits for the mantissa. And we're always going to assume the leading digit to be a 1, because with the leading digit to be a 1, because in normalized scientific notation, the leading digit can't be a 0. Okay. All right, and then so I think we did this example. I said compare your answers with a neighbor, but or maybe this is a new one. Okay, but we'll just go through it quickly. Okay, so 0, 1, 0. This is going to be our exponent. Okay, we have a 1 for the sign, so this is going to be a negative number. 0, 1, 0 is the exponent. What is this in binary? It's 2, right? 1, 0 is a 2. Okay, our exponent, our bias is 3, so we do 2 minus 3. Our exponent is going to be -1. So we have 2 to the -1 for the exponent. And here I've got 1, 0, 1, 0. So I've got 1.1010. Okay, so this is what we have right now. We have 1.1010 and 2 to the -1. Is that okay? And it's a negative number. Are we okay going from this? The last 4 is going to be the last 4 in our mantissa. This one makes it a negative. And then this here is the exponent, which is equal to 2. The bias is 3. And so we have 2 to the -1. Are we okay getting to this point? Just give me a nod your head. All right. Okay. Some of you nodded your head. So that's good. Okay. And then so now we have to convert this to, a decimal. All right. So here I've got a negative and we've got 1. And then the 0.1 is 1/2. And then this one here, this is 1/8. Okay. So I've got 1 plus 1/2 plus 1/8. Right. And that becomes -13/8. Is that all right? -13/8. 2 to the -1 is multiplied by 1/2. So this is going to become -13/16. And our number is going to be -0.8125. Okay. So we will, so that's our answer. Okay. If you want, you could also roll the binary point. So instead of doing 1 plus 1/2 plus 1/8 times 1/2, okay. Oops. You can also just kind of roll the binary point 1 space over to the left. And now we have 0.11010. And this is 1/2 plus 1/4 plus 1/16. And we'll also get the same answer of -13/16. Okay, a couple ways to get our answer here. All right. With the specification that we've with it so far, we run into a problem. Okay. What if you have all zeros here? All zeros. What number should this represent? Okay. Intuitively, we feel like this should represent 0. Okay. But does it represent 0? It actually doesn't. Okay. The sign bit's 0, so it's positive. The exponent bits are 0. Okay. So the exponent's -3. And the mantissa bits are all 0. Okay. So with the leading 1, okay, this becomes 1.000. And we have 2 to the -3. And so this becomes 1/8. Right. So this is what we don't want this. Okay. We want to somehow, we don't have a way to represent 0. We don't have a way to represent 0 because right now we said the leading bit is always going to be a 1. All right. So we actually have to introduce, this is the special case. Okay. The special case is when the exponents are all 0. Okay. When the exponents are all 0, we're going to change to denormalized mode where the leading bit is no longer a 1. Okay. So, it was useful for us to assume that in kind of normalized binary scientific notation, there's always going to be a leading 1. Okay. And that kind of reduces redundancy because, there's no need to kind of keep a 1, use up one of our mantissa bits to kind of always say that there's a 1, because that's going to be the case for almost all of the cases. But there's the problem in that if the leading bit is always a 1, we don't have a way to represent 0. Okay. And so what we have to do is we introduce denormalized mode. And in denormalized mode, when the exponent bits are all 0, then what happens is that the digit in front of the mantissa bits is 0. Okay, the digit in front of the mantissa bits is 0. Okay, and so when we do that, when we switch from 1 to 0, okay, there's if we just leave everything else the same, there's going to actually end up being kind of like a jump in the numbers. I call this a discontinuity in the numbers. Okay, and so when you're in denormalized mode, I mean, it feels confusing, but we have to do it this way, otherwise it's not going to work. In denormalized mode, the exponent bias is going to be 1 less than normal. Okay, and so for a mini floating point system, the exponent bias is not 3, but it's going to be 2. It's going to be 2 in denormalized mode. Okay, and if you're talking about the double precision floating point, where your exponent bias is normally 1023, when you're in denormalized mode, your exponent bias is 1022. Okay, and it's just like kind of an extra rule, and it accounts for the fact that the leading bit is no longer a 1, but it's now a 0. Okay, and so when you do that, you have to kind of change what the exponent bias is going to be. All right, and so in this case, it now works. All right, so if the exponent bits are all 0, this is our special case. We are now in denormalized mode. Our bias is going to be 1 less than normal, which is going to be 2. And so with a bias of 2, the exponent is now -2 rather than -3. And so the mantissa bits are all zeros. The leading bit is 0. And so we're going to have 0.000, which is going to be 0 times 2 to the -2. So having all zeros now represents the number 0. Is that all right? I mean, I'm just kind of talking and you guys are following along. So let me give you your first quiz answer for today. First quiz answer is the letter A. A as an apple. A as an apple. All right. Is it still possible to represent 0.125? Yes, we can do it. I don't know off the top of my head, but we can do it. Okay. And then a question. So even if the mantissa bits have 1s in the exponent bits, it will still be calculated in denormalized mode? Yes. Okay. So if the exponent bits are all 0, okay, then it's in denormalized mode, and you can put in numbers here. So I think if this is a 1, it's going to be 1/8. Okay, 0.125, because then we have a 0.1000, right? So if I replace this with a 1, everything else is the same. This is a 1. We're going to have 0.1000 times 2 to the -2. So this would be 1/2 times 2 to the -2 is 1/4, and that would be 1/8. Okay, we'll have a few more examples, okay, of denormalized mode. Okay, and then the other exponents case, special exponents case, is when the exponents are all 1s. Okay, if the exponents are all 1s, it has special meaning. Okay, if the exponent bits are all 1s and the mantissa bits are all 0, that represents infinity. Okay, that represents infinity. And you have a positive infinity and you have a negative infinity. And then if the exponent bits are all 1s and you have anything other than all 0s in the mantissa, then you end up with not a number. Okay, so not a number is a floating point number, or it's represented in floating point. And it's just if the exponent bits are all 1s, but you have something other than all 0. Okay, if you have anything other than all 0, it's going to become not a number, or nan. Okay, this is the smallest non-zero value we can represent. Okay, we have this, I guess, the smallest positive non-zero value we can represent. Okay, we have 0 positive, 0, 0, 0. Exponents are all zeros. This is denormalized mode. and this is our mantissa, okay? So what number is this, okay? The mantissa bits are 0.0001, okay? And we're in denormalized mode, so the leading digit is a 0. So I've got 0.0001. So what is that? This is 1/2, 1/4, 1/8, 1/16. Okay, so this portion represents 1/16, and my exponent is 2 to the negative 2. So I've got 1/16 times 1/4. The smallest number I can represent with this mini float representation is 1/64. Okay, so this is denormalized mode because the exponent bits are all 0. Anytime you have the exponent bits are all 0, it's denormalized mode, okay? It's a special case, right? Exponent bits all 0 is a special case. Exponent bits all 1 is a special case. All 1 means it's either going to be infinity or not a number. All 0 puts us in denormalized mode. So we have the exponent bits here. We have all 3 exponent bits are 0, so it's denormalized mode. If you're in a type double, you have 11 exponent bits. If all 11 of those are 0, you're in denormalized mode, okay? And in denormalized mode, the bias is 1 less than usual, okay, which is a negative 2. These are just the rules, okay, for how it works. But is this okay? Going from here to 1/64? Okay. All right. So what's the next smallest number we can represent? Okay. The next one would be this. Okay. So if you're counting, so this is now a 2. So this is basically going to be 2/64. Okay. So this is 0, 0. Okay. 0, 0, 1, 0. This is 1/2, 1/4, 1/8, and 0/16. Okay. So we have 1/8 times 2 to the negative 2. So 1/8 times 132, or I mean 1/4 is 1/32. Okay, which is equivalent to 2/64. All right. So the increment from the smallest to the next smallest value is 1/64. Okay. And we're basically going to be counting by 64ths for a little while. Okay. So, and then the next value, okay, 0, 1, 1, okay, 0, 0, 1, 1 becomes 3/64. 0, 1, 0, 0 becomes 4/64. 0, 1, 0, 1, 5/64. 0, 1, 1, 0, 6/64. So this, I hope you guys are getting comfortable counting in binary. Okay, this is 4 and 2 and 0 makes 6, right? And so we're basically just incrementing by 64ths. So we go from 1/64, 2/64, 3/64, 4/64, 5/64, 6/64. Yeah, I mean 4/64 is 1/16 and things like that, but we're just incrementing by 1/64. Okay. What happens to all of the values in between? Yeah, you can't represent them, right? So if you want to represent something like 3.5/64 or 7 1/28, you can't. You cannot. All right. Just like, so here I brought my little calculator. Okay. The smallest number I can represent here is 0.0000 1, 2, 3, 4, 6 zeros and a 1. That's the smallest number I can possibly represent. Okay. I cannot. Can I represent anything smaller? I can't. I can't. Okay. Like if I do this divided by 2, it tells me it's 0. Okay. Now that's not the case, but I'm not able to represent anything smaller. Okay. This is the largest denormalized value that I can represent. Okay. The largest denormalized value is going to be all zeros here. 1, 1, 1, 1. Okay. So 1, 1, 1, 1. I got 15. All right. So 0.111. This is 15/16 multiplied by 2 to the negative 2. So this is 1/4. So this becomes 15/64. 15/64. Is that all right? So that's the largest denormalized value. And then the next value, right? So here, if you're looking at this, if you're just looking at this, then the next thing that comes, this is going to naturally just become a 1 here. And we get 1, 0, 0, 0. Okay. So now our exponent bits are all 1s. Okay. The exponent, I mean, not all 1s. Exponent bits are 0, 0, 1. Okay. So this is going to be the smallest exponent we have that is still normalized. Okay. So now we use our regular bias, which is 3. Okay. All right. And with the bias of 3, the exponent is negative 2. All right. So this part still remains the same. I'm still multiplying by 2 to the negative 2. Okay, but now this these parts now have a 1 in the leading in the mantissa. Okay, the leading digit in the mantissa is now a 1. So now I have 1.0000, and this is times 2 to the negative 2. This is just equal to 1 times 1/4, right? And this is 16/64, okay, or 1/4. So we've gone from 15/64 to 1/4 or 16/64. Sorry, let me tend to my dog. Okay. All right, and then so the next value that we would count, okay, it's going to be 001, 0001. Okay, so the exponent bits are 001. So this is going to be exponent of negative 2. The mantissa bits are 0001. Okay, so now we have 1.0001. And we multiply by 2 to the negative 2. This is 1 plus over here is 1/16. And so this becomes 17/16 times 1/4. And we have 17/64. Okay, so the next increment is still 1/64. Okay, and then if you keep going, this will become 18/64, 19/64, 20/64, 21/64, 22/64, so on and so forth. Okay. And then, all right, so if you keep going, you'll eventually come to here. All right. And so if I have 001 in the exponent and my mantissa bits are 1111, this number is going to be 1 plus 15/16 times 2 to the negative 2. So times 1/4. Okay. So this over here becomes 31/16. This right here, I multiply that by 1/4, and we get 31/64. Okay, I feel like so far, it doesn't seem impressive at all because I'm just counting by 64ths and you're just like, all right, we get it. You're counting by 64ths. Okay, but this is the genius. This is the genius of floating point numbers. Okay, and the next thing you will see, okay, what is the next number that we count? Okay, the next number. So here I have 31/64. So naturally, what's the next number going to be? 32/64, right? 32/64 is 1/2, right? So 1/2 is represented with this 010 in the exponent, okay? And now our bias, right? So this represents 2. Our bias is 3. The exponent is going to be -1. These are all zeros. So we have 1.0000, okay? So 1 times 2 to the negative 1. And we get 1/2 or 32/64. Okay. All right. But what is this number? Okay. The exponent bits are 010. Okay. So our exponent with our bias is 3, our exponent is -1. Okay. The mantissa bits are 0001. The leading digit is 1. So I have 1.0000. I'm sorry, 0.0001. So this is 1 plus 1/16. And I'm multiplying by 2 to the negative 1. I'm multiplying by 1/2. So here I have 17/16. And I'm multiplying by 1/2. So this is 17/32, or the equivalent of 34/64. Okay. So we went from 31/64 to 32/64, but now we jump up to 34/64. Okay. And if you wanted to represent 33/64, it is not possible. You cannot represent the number 33/64. You can either represent 32/64, which is 1/2, and that's this set of bits. And the next smallest number you can represent is 34/64 or 17/32. Is that okay? And so the increments, as the numbers get bigger, in the beginning we were counting by 1/64, but after we got to 1/2, now we're going to be counting by 30 seconds. and we keep counting. The next number is going to be 18 30 seconds. Okay, and then we get 19 30 seconds, 20 30 seconds, 31 20 30 seconds. I mean 21 30 seconds, 22 30 seconds. Okay, so what's the biggest number I can represent with 0 1 0 in the exponent? Okay, the largest value I can represent with 0 1 0 in the exponent is going to be 1 1 1 1, and that's going to be 31 30 seconds. Okay, so we're incrementing now by 30 seconds. Okay, so what's the next number? The next number is 32 30 seconds or 1. Okay, and it's going to look like this. Okay, 0 1 1. This is 3. Okay, with a bias of 3, this becomes 0, and I have a bunch of zeros here. All right, and so this is going to become 1.000 times 2 to the 0. That's just 1, 32 30 seconds. Okay, and so then if I increment this, what is that going to be? So if I change this number to a 1, what's the next number going to be? Put it in the chat if you think. 17 16ths. Yeah, we're incrementing by 16ths now. Okay, we're no longer incrementing by 30 seconds. We're now incrementing by 16ths. Okay. And this allows us to represent a range of numbers rather than being, because if we were stuck on incrementing by 64ths, okay, then like the biggest number we could represent would be like 2. Okay, we would get, I mean, this isn't going to be much better, but we can represent things that are bigger, right? So now our increments are going to be 1/16. We're at 17 16ths, okay? And it keeps going, 16 16, 17 16, 18 16, 19 16, and then we get up to here, and this is going to be 31 16ths. Okay, and then the next number is going to be 2. All right, and then I think you figured out the pattern by now. Instead of incrementing by 16ths, we're going to be incrementing by 8ths. Okay, so we have 16 eighths, which is 2, 17 eighths, 18 eighths, 19 eighths, and we get up to here, which is going to be 31 eighths. Okay, and the increment here is going to be 1/8, and then at the next spot, we're going to be incrementing by 1/4, right? So is this okay? So this is like, we're just counting in binary, just rotating things. So we increment by 16ths, then we increment by 8ths until we get to 31 over 8. And then we increment by 4ths until we get to 31 over 4. Okay, which is just shy of 8, right? So 16 over 4. So this represents the number 4. This represents 4 1/4. You cannot represent any number between 4 and 4 1/4. 4 and 4.25. After 4, the next number is 4.25, then 4.5, then 4.75, and then 5. Okay. If you wanted to represent 4 1/8, it's impossible. Okay. You cannot do it with the number of bits that we have in this floating point system. Okay. And then we get up to here, 31/4, which is 7 3/4. And now we're at 8. Okay. And we keep going until we get up to here, which is 31 halves. And this is 15.5. Okay. And then what is the next number after this? The next number after this is 111,000. And according to our floating point system, when we have 111 for the exponent and all zeros, this is infinity. Okay, so kind of in our last bit, the increment between values is 1/2. Right, so we get 8, 8.5, 9, 9.5, 10, and we get up to 15.5, and then after that, it's infinity. So it seems silly, but the biggest possible number we can represent is 15.5. And if you say, well, what's 15.5 plus 1/2? It's going to say, oh, it's infinity, right? So according to this mini float system, the next, if you say, what's 15.5 plus 1/2, it's going to come back and say it's infinity. Okay. And that seems silly, but that's how it's set up. How do we feel about this? Yeah, not a number is if one of these bits is not a 1, not a 0. Okay, so if it's all ones in the exponent and something other than all zeros, then it becomes not a number. So there's multiple ways to express not a number. Yeah, all combos that aren't all zeros, any combo there that's not all zeros is not a number. Okay, let me give you the next quiz answer. Next quiz answer is C. C as in cat. C as in cat. Second quiz answer. C as in cat. Okay. Is this all right? Let's see. We have a question. Does this mean computers are less precise in approximating larger numbers? Yes, absolutely. Like if you have some limited number of bits, you might be able to represent 0.001, yes, but you cannot represent 500.001. Yes, absolutely. That is absolutely the consequence of the floating point system. Okay. So for example, and if you use an old calculator like this, did you ever have an old calculator like this, or did you always have like a super fancy thing, right? Okay, so on the old calculator, you can represent a number as small as 0.0001, right? You can represent this, and you can increment by this, right? But can you represent 1,000 with 8? You like, so this is 0.00001, but can you represent 100.00001? You cannot, right? Like if you have 100 in the front, because there's only 8 digits, you can't have 8 digits after the decimal place, right? And it's kind of like that, right? So yes, so as the numbers get bigger, you have less precision. You cannot keep as many decimal places. Okay, absolutely. Yeah, if you have a 1 here, if this becomes a 1, this becomes negative infinity. Okay, this becomes negative infinity. All right, so let's just talk some of the things, right? So for the double precision floating point, we have sign bit 0, 11 bits for the exponent, okay? And the mantissa, we have 51 bits, okay? 51 0 bits, okay, followed by 1 bit. This is the smallest positive non-zero value. Smallest positive non-zero value. Okay, so we have 0.000. We're in denormalized mode, okay? Our exponent, the bias is 1 less than normal. So we're going to have times 2 to the negative 1022. Okay, so the absolute smallest number is 1 times 2 to the negative 1074. Let me bring this over here. Let me make this bigger for you guys. Okay, so this is the smallest number you can ask for, 2 raised to the negative 1074. All right. If you ask for anything smaller than that, 2 to the negative 1075, it's going to come back 0. Okay. If you ask, what is this? What is this divided by 2? It says it's 0. Okay. Now, obviously, we know that it's not 0, but the computer can't represent anything smaller than this. Okay. And then the next smallest, the smallest normalized value. Okay. The smallest normalized value is 2 to the 10, 1 times this with the regular bias, 2 times negative 10, 2 to the negative 1022, all right? 2 to the negative 1022, and this is the smallest normalized value, okay? This is, you can ask for dot machine. This tells you all of the properties of the kind of computer system here, all right? And so you can ask for x machine dot double x min, okay? And that's this number, 2.225 times 10 to the negative 308. Okay, this is the smallest normalized value we can represent. Okay, this is the smallest denormalized value. Anything smaller than this will return 0. This is the smallest normalized value. All right, and so, you know, if you type in dot machine, and you can dot machine $ double, and you can ask for other things, right? So dot double x min is this, x machine dot double x max is a different number, okay? So that's where this number comes from, all right? The next normalized value, next smallest normalized value is basically this plus 2 to the negative 52, right? Because if I have 51 0 bits, we have 52 bits to represent the mantissa. So I can have 1.000, 51 zeros, and then a 1, and these are going to be distinct values. All right, so let me just do. All right, so I can do, well, so we have this here. Okay, so this is the smallest normalized. And then if I do this can be represented, okay? And we have that. And these are going to be distinct. Is x equal to y? That's not going to be true. These are not equal to each other, okay? But if I try to do like a different comparison, okay? Well, here, let me just show you. So if I do z is equal to 1 plus, if I try to add a smaller increment, 2 to the negative 53, okay? If I try to do this times 2 to the negative 1022, okay? If I say, okay, so here's z, if I say is x equal to z, that's going to come back true, all right? So if I try to add on an increment smaller than 2 to the negative 52, because I only have 52 bits in the mantissa. So if I try to add on anything smaller than that, the computer cannot tell the difference. Okay, the computer is not able to represent the difference between x and z. And so even if I say z is equal to this, all right, it can't represent that, and it's going to come back and say x and z are equal to each other. All right, is that okay? So this difference, okay, the difference between this number and this number, this is known as machine epsilon, okay? Because this is the smallest number you can represent, 2 to the negative 52. This is the smallest thing that you can add to 1, and the machine will still recognize that it's different from 1, 2 to the negative 52, okay? This is known as machine epsilon. And so if you try to add on anything smaller than this, the computer is going to think of it as the same number. So if you do 1 plus anything smaller than machine epsilon, it's going to just say it's still 1, okay? If you add machine epsilon, then it can distinguish the two values, right? So here I've got, so if I say 1 equals 1, okay, so here's 1, and I can do 1 plus 2 to the negative 52, right? And that's a different number. If I try to add something smaller than that, it's going to give me, it's going to come back as 1, okay? If I do this equal to 1, that's going to come back true. If I add on machine epsilon, then they're going to say it's different. Is that all right? So these are things you got to be aware of. You got to be aware of like how much, when your computer can no longer distinguish things. Okay. So this is all to say. Here's x. X is 1. If you add 2 to the negative 52, these are distinct values. Okay. You add anything smaller than that. A is 1. B is 1 plus 2 to the negative 53. The computer is going to say these two things are the same. You basically added nothing, okay? And the computer is able to represent 2 to the negative 53. It has no problem representing that, right? It has no problem, okay? But you cannot add 1 plus 2 to the negative 53, okay? And have it distinct from 1. Does it? There's a difference there, okay? It's not that the computer thinks this is 0, okay? The computer doesn't think this is 0. It knows 2 to the negative 53 is this number. It knows that. But it has only a limited amount of precision. And so if you try to add this number, 2 to the negative 53 to 1, it doesn't have space to keep it, right? Because the consequence, of the thing is that, at one point, you're able to represent numbers as small as 1/64. But then when you get to a certain point, your increment size is 1/4 or 1/8 or something like that. And if you try to add numbers smaller than that increment, it can't represent it. Okay, and that's what we have here. Does that make sense? What's happening? Okay, so in the number 1 is represented with this. So is machine epsilon the same in other programming languages? Machine epsilon for a double precision will be the same for all programming languages. It's going to be the same for, so pretty much all computers conform to this IEEE 754 hardware specification. And the number handling is handled at a hardware level. So, you know, your cell phone, whether you're programming on your cell phone or programming on an Apple or a PC, and whether you're using Java or C or R, this is how it handles numbers. And double precision is going to have the same kind of machine epsilon. But if you use like single precision, it's going to be different, right? If you use different levels of precision, it's going to be different. This is not number theory. This is just how the computer represents numbers in the thing. Okay, so let me just show you a few more things. Okay, so that's the number 1. This is 1 plus machine epsilon, right? All zeros and then a 1, okay? And so if you try to represent 2 to the negative 53, we don't have enough spaces in the mantissa to represent that number, okay? All right, so here's a question. Here's a question. Yeah, you can only do 2 to the negative 52 because there's 52 bits in the mantissa, right? If we had more numbers in the mantissa, we could represent more than that, right? But we only have 52 bits in the mantissa. That's what we've chosen. So that's as small as we can go, okay? All right, so here's a thought experiment. Let's say I run this, right? We're just going to start off with x equal to 0, and we're going to do x, and we're going to do x plus 1. And I'm going to just let the computer run for like 10 years, okay? And I come back and I say, hey, what number do you reach? What do you think the computer will reach? Yeah, okay. So it doesn't reach infinity. It doesn't reach double x max. It gets stuck at 2 to the 53. It gets stuck at 2 to the 53. Okay, so let me just kind of show you, right? So here's a big number, all right? And I'm going to just kind of run this. And, wipe everything out of here. Okay, so here's x, and then I'm going to add 1 to x, okay? All right, and let's add 1 to x, then 0.992, and I add 1 to x, and it's stuck. It doesn't get any bigger than 900 whatever 992. Do you see that? Adding 1 doesn't change the value, okay? And the issue is that when it reaches 2 to the 53, the step size becomes 2. The step size becomes 2. And so now we can no longer add 1, right? So that, you know, when we had 1, the step size was 2 to the negative 52. We couldn't add anything smaller than 2 to the negative 52, right? When we get to this number, 2 to the 53, the step size is no longer 1. The step size is now 2. And so we cannot add increments smaller than 2. So I am able to add 2 to this, and the computer is able to recognize that, hey, if you add 2, that works. But if I try to add 1 to this, it gets stuck, okay? It has a weird thing of handling kind of things, but you can keep adding 2 and it'll keep counting, okay? So you can't add 1, but you can add 2, okay? Because the step size is now 2. Is that all right? Okay, so this is going to be the largest possible value that we can represent in type double. Okay, we have 0 for the positive, 0's positive sign bit, almost all 1s. Okay, 1 1 1 1 1, but a 0. Okay, so that's not going to be infinity. All right, this is the largest possible value that's not infinity, and then all 1s in the mantissa. Okay. And so this, if I do it, okay, basically from 0 to the negative 52, all right, we're going to take all of that and we're going to multiply by 2 to the 1023, all right? All right, and this is the biggest number I have, right? And this is double x max. This is known as machine double x max, the largest value that we can represent, okay? Anything bigger than this becomes I'm sorry. So if I try to add this, then, so if I try to add 2 to the 969, it doesn't recognize that. It's going to say that's exactly the same as before. If I add 2 to the 970th, it becomes infinity. This got cut off. All right. So double X max is this number. Okay, that's double X max. If I do a plus 2 to the 969, it comes back. It's actually no different than before. But if I try to add 2 to the 970, it comes back as infinity. All right. So anything larger becomes infinity. All right. And so what we have to do is, because everything is approximate and we can't represent real numbers, stuff like this breaks, right? When we do 0.1 plus 0.2 and we say, is that equal to 0.3? We get back false, all right? These things are not, this isn't true, okay? And so an alternative is we can use something called all equal, okay? All equal will return true if the difference between them is less than 10 to the negative 8, okay? It takes the square root of machine epsilon, and so then it just says, if it comes back within square root of machine epsilon, we're going to say these two things are equal, okay? So we can say, is 0.1 plus 0.2, is that equal to 3? Then it comes back as true, right? Whereas this, because we've got approximate representation, it's not true. Here we've got, all right, so anyway, this stuff, if you add 2 to the negative 52, okay, these are not equal, okay? But if you use all equal, it's going to say, yeah, these are approximately equal. These are close enough, okay? And so these are more things. So this is kind of, if you add 2 to the negative 26, this will be seen as equal. 2 to the negative 25, this is when it's going to say it's no longer equal, okay? So it will allow up to this much difference, and it will say they're equal. But once it's a little bit bigger, then all equal will say it's not equal, okay? And this is just the default settings for all equal. You can change kind of the tolerance level yourself if you want to. Okay, the unfortunate thing is that all equal doesn't return true or false. It returns back this gibberish, okay? Mean relative difference is this, all right? Sometimes you just want a true or false, and then you can just do is true all equal, and that will come back either true or false, all right? Is that all right? Okay, so that's the summary of floating point numbers. So the cutoff to infinity is, this is the largest number we can represent. This is known as machine double max, and it's the sum of all of this, okay? All right, let me stop the recording here, but I wanted to say, wish you guys a happy Valentine's Day. So wait, let me give you your last quiz answer. Last quiz answer is D. D as in dog. D as in dog is your last quiz answer. Okay.